Welcome. Today, we're diving into the fascinating world of neural networks. These powerful systems are at the heart of modern artificial intelligence, enabling computers to learn from data and make decisions in ways that mimic the human brain. Whether you're new to the topic or looking to refresh your knowledge, this journey will help you grasp the core ideas behind neural networks, their structure, and why they're so important in today's technology landscape. Let's start by exploring what neural networks are and how they fit into the broader field of AI. Neural network is a computational model inspired by the way biological brains work. It consists of interconnected nodes or neurons that process information in layers. Each neuron receives input, performs a calculation, and passes the result to the next layer. This structure allows neural networks to recognize patterns, make predictions, and solve complex problems. By adjusting the connections between neurons, the network learns from data, gradually improving its performance over time. This adaptability is what makes neural networks so powerful in fields like image recognition and natural language processing. Neural networks draw inspiration from the human brain's structure. In our brains, billions of neurons communicate through electrical signals, forming intricate networks that enable thought, memory, and learning. Similarly, artificial neural networks use mathematical functions to simulate these connections. While they're much simpler than real brains, the basic idea is the same. Information flows through layers, and learning happens by adjusting the strength of connection. This biological analogy helps us understand why neural networks are so effective at tasks that require pattern recognition and decision-making. Typical neural network is organized into layers. The first layer, called the input layer, receives raw data. Next come one or more hidden layers where most of the processing takes place. Finally, the output layer produces the network's prediction or decision. Each layer is made up of neurons that are connected to neurons in the previous and next layers. The number of layers and neurons can vary depending on the complexity of the problem. This layered structure is key to the network's ability to learn and generalize from data. In a neural network, each neuron acts as a tiny processor. It takes input values, applies a mathematical function, and sends the result to the next layer. Neurons are connected by weights, which determine how much influence one neuron has on another. During training, these weights are adjusted to minimize errors and improve the network's accuracy. The collective behavior of thousands or even millions of neurons working together allows neural networks to tackle complex tasks that would be difficult for traditional computer programs. Weights and biases are the key parameters in a neural network. Weights determine the strength of connections between neurons, while biases allow the network to shift activation thresholds. By adjusting these values during training, the network learns to map inputs to outputs more accurately. Think of weights as tuning knobs that control how much each input matters, and biases as fine-tuning adjustments. Together, they enable the network to model complex relationships in data, making neural networks highly flexible and powerful. Activation functions play a crucial role in neural networks. After a neuron processes its inputs, the activation function determines whether and how much of the signal should be passed on to the next layer. Common activation functions include sigmoid, tan, and ReLU. These functions introduce nonlinearity, allowing the network to learn complex patterns beyond simple linear relationships. Without activation functions, neural networks would be limited in what they could represent and solve. Forward propagation is the process by which input data move through the network, layer by layer, until it reaches the output. At each step, neurons process the data, apply activation functions, and pass the results forward. This flow of information allows the network to make predictions based on the current state of its weights and biases. Forward propagation is essential for both making predictions and for the training process, as it sets the stage for learning from errors. Loss function measures how far the network's predictions are from the actual values. It's a mathematical way to quantify errors. During training, the network aims to minimize this loss by adjusting its weights and biases. Common loss functions include mean squared error for regression tasks and cross-entropy for classification. The choice of loss function depends on the specific problem being solved. By minimizing loss, the network improves its accuracy and becomes better at making predictions. Backpropagation is the key learning algorithm for neural networks. After forward propagation, the network calculates the loss. Backpropagation then works backward through the network, computing how much each weight contributed to the error. Using this information, the network updates its weights to reduce future errors. This process is repeated many times, gradually improving the network's performance. Backpropagation is what enables neural networks to learn from data and adapt to new information. Training a neural network involves feeding it data, calculating predictions, measuring errors, and adjusting weights through backpropagation. This cycle repeats over many iterations, known as epochs. With each epoch, the network becomes better at mapping inputs to outputs. Training can take anywhere from minutes to days, depending on the size of the network and the complexity of the data. The goal is to find the set of weights and biases that minimize the loss and maximize accuracy. Two common challenges in training neural networks are overfitting and underfitting. Overfitting happens when the network learns the trained data too well, including noise, and fails to generalize to new data. Underfitting occurs when the network is too simple to capture the underlying patterns. Balancing these issues is crucial for building effective models. Techniques like regularization, dropout, and using more data can help prevent overfitting and improve generalization. Regularization techniques help prevent overfitting by adding constraints to the network. Common methods include L1 and L2 regularization, which penalize large weights, and dropout, which randomly disables neurons during training. These techniques encourage the network to learn more general patterns and avoid relying too heavily on specific features. Regularization is an essential tool for building robust neural networks that perform well on new, unseen data. Learning rate is a crucial parameter in training neural networks. It determines how much the weights are adjusted during each update. A learning rate that's too high can cause the network to overshoot optimal solutions, while one that's too low can make training painfully slow. Finding the right learning rate is often a matter of experimentation and can significantly impact the network's ability to learn effectively. Batch size refers to the number of training examples processed before the network's weights are updated. Smaller batch sizes can lead to more frequent updates and faster learning, but may introduce more noise. Larger batch sizes provide more stable updates but can slow down training. Epochs represent the number of times the entire dataset is passed through the network. Together, batch size and epochs control the pace and thoroughness of learning. There are several types of neural networks, each suited to different tasks. Feed-forward neural networks are the simplest, with data flowing in one direction. Convolutional neural networks (CNNs) excel at image processing, while recurrent neural networks (RNNs) are designed for sequential data like text or time series. Each type has unique strengths and applications, making neural networks a versatile tool in the AI toolkit. Feed-forward neural networks are the foundation of many AI systems. In these networks, data moves in one direction from input to output without loops. They're used for tasks like classification and regression, where the goal is to map inputs to outputs. While simple, feed-forward networks can solve a wide range of problems and serve as the building blocks for more complex architectures. Convolutional neural networks, or CNNs, are specialized for processing grid-like data such as images. They use convolutional layers to automatically detect features like edges, shapes, and textures. CNNs have revolutionized computer vision, enabling breakthroughs in image recognition, object detection, and more. Their ability to learn hierarchical features makes them ideal for tasks involving visual data. Current neural networks, or RNNs, are designed to handle sequential data. Unlike feed-forward networks, RNNs have loops that allow information to persist across time steps. This makes them well-suited for tasks like language modeling, speech recognition, and time series prediction. RNNs can remember previous inputs, enabling them to capture context and dependencies in sequences. Deep neural networks are simply neural networks with many hidden layers. The depth allows them to learn more complex and abstract features from data. Deep learning, which uses these networks, has powered advances in fields like speech recognition, natural language processing, and autonomous vehicles. The more layers, the greater the network's capacity to model intricate relationships. Neural networks have transformed image recognition. From identifying objects in photos to enabling facial recognition, these systems can process vast amounts of visual data with remarkable accuracy. Convolutional neural networks, in particular, have made it possible for computers to see and understand images in ways that were once thought impossible. This technology powers everything from smartphone cameras to advanced medical imaging. Neural networks are also at the core of natural language processing (NLP). They enable computers to understand, interpret, and generate human language. Applications include language translation, sentiment analysis, and chatbots. Recurrent and transformer-based networks have made it possible for AI to grasp context, meaning, and even nuances in text, making communication with machines more natural than ever. Speech recognition systems rely heavily on neural networks. By analyzing audio signals, these networks can convert spoken words into text, enabling voice assistants and transcription services. Advances in deep learning have dramatically improved the accuracy and speed of speech recognition, making it a common feature in smartphones, smart speakers, and customer service applications. Neural networks play a critical role in autonomous vehicles. They process data from cameras, sensors, and radar to understand the environment and make driving decisions. Deep learning enables these vehicles to recognize objects, predict movements, and navigate safely. The combination of neural networks and real-time data processing is paving the way for safer, smarter transportation. Healthcare neural networks are revolutionizing diagnostics and treatment planning. They can analyze medical images, detect diseases, and even predict patient outcomes. By learning from vast datasets, these systems assist doctors in making more accurate diagnoses and personalizing care. Neural networks are helping to improve patient outcomes and streamline healthcare processes. Neural networks are widely used in finance for tasks like stock price prediction, risk assessment, and fraud detection. By analyzing historical data and identifying patterns, these systems can make forecasts and flag unusual activity. Their ability to process complex, nonlinear relationships makes them valuable tools for financial analysts and institutions. Neural networks are making games and entertainment more immersive and intelligent. They power non-player characters, adapt gameplay to individual users, and even generate new content. In music and art, neural networks can compose songs, create paintings, and enhance creativity. This blend of technology and creativity is opening up exciting new possibilities in entertainment. Despite their power, neural networks face several challenges. Training large networks requires significant computational resources and data. They can be sensitive to the quality of data and may struggle with interpretability, understanding why a network made a particular decision. Addressing these challenges is an active area of research, with ongoing efforts to make neural networks more efficient, transparent, and robust. Interpretability refers to our ability to understand how a neural network makes decisions. As networks become more complex, it becomes harder to trace the reasoning behind their outputs. Explainable AI aims to make these systems more transparent, providing insights into their decision-making processes. This is especially important in fields like healthcare and finance, where trust and accountability are critical. Neural networks typically require large amounts of data to learn effectively. The quality and diversity of this data directly impact the network's performance. Insufficient or biased data can lead to poor generalization and unintended consequences. Collecting, cleaning, and curating data is a crucial step in building successful neural network models. Training neural networks, especially deep ones, demands powerful hardware. Graphics processing units, GPUs, and specialized chips like TPUs accelerate the training process by handling massive parallel computations. Advances in hardware have made it possible to train larger and more complex networks, fueling rapid progress in AI research and applications. Transfer learning is a technique where a neural network trained on one task is adapted for another related task. This approach saves time and resources by leveraging existing knowledge. For example, a network trained to recognize animals can be fine-tuned to identify specific breeds. Transfer learning is especially useful when data for the new task is limited. Reinforcement learning is a branch of machine learning where neural networks learn by interacting with an environment and receiving feedback in the form of rewards or penalties. This trial-and-error approach enables networks to develop strategies for complex tasks, such as playing games or controlling robots. Reinforcement learning has led to impressive achievements, including AI systems that outperform humans in games like Go and chess. Generative neural networks such as generative adversarial networks (GANs) can create new data that resembles the training data. They're used for tasks like image synthesis, style transfer, and data augmentation. GANs consist of two networks, a generator and a discriminator, that compete to improve each other. This creative capability is opening up new frontiers in art, design, and data science. As neural networks become more integrated into society, ethical considerations are increasingly important. Issues like bias, privacy, and accountability must be addressed to ensure fair and responsible use. Researchers and practitioners are developing guidelines and tools to promote transparency, fairness, and ethical decision-making in AI systems. Future of neural networks is bright, with ongoing research pushing the boundaries of what's possible. Advances in architectures, training methods, and hardware are enabling new applications and greater efficiency. As neural networks become more capable and accessible, they'll continue to transform industries and shape the way we interact with technology. Neural networks are already part of our daily lives, often behind the scenes. They power recommendations on streaming platforms, filter spam and email, and enable features like voice search and photo tagging. As these systems become more advanced, their impact on our routines and experiences will only grow, making technology more intuitive and helpful. Getting started with neural networks is easier than ever, thanks to user-friendly tools and libraries. Platforms like TensorFlow and PyTorch provide building blocks for designing, training, and testing models. Beginners can experiment with simple datasets and gradually tackle more complex problems. The key is to start small, learn the basics, and build confidence through hands-on practice. There are countless resources available for learning about neural networks. Online courses, tutorials, and books cover everything from the basics to advanced topics. Communities and forums offer support and guidance for learners at all levels. By taking advantage of these resources, anyone can develop a solid understanding of neural networks and their applications. In working with neural networks, it's important to avoid common pitfalls. These include using insufficient data, neglecting to pre-process inputs, and overcomplicating models. Careful planning, thorough testing, and continuous learning are essential for building effective neural network solutions. By being mindful of these challenges, you can set yourself up for success. Experimentation is a key part of working with neural networks. Trying different architectures, parameters, and training strategies can lead to better results. Don't be afraid to iterate and learn from mistakes. Each experiment brings new insights and helps refine your understanding of how neural networks work. AI research is a collaborative effort, with scientists, engineers, and enthusiasts working together to advance the field. Open-source projects, shared datasets, and community-driven initiatives accelerate progress and make knowledge accessible to all. By collaborating, we can tackle bigger challenges and unlock the full potential of neural networks. The field of neural networks is evolving rapidly, with new breakthroughs and techniques emerging all the time. Staying informed through research papers, conferences, and online communities is essential for anyone interested in AI. Continuous learning ensures you remain at the forefront of this exciting and dynamic field. Let's recap what we've covered. Neural networks are powerful models inspired by the brain, capable of learning from data and making complex decisions. We explored their structure, training process, types, and applications across various fields. Understanding the fundamentals of neural networks opens the door to a world of possibilities in artificial intelligence and beyond. As we look to the future, neural networks will continue to shape the way we live, work, and interact with technology. Their ability to learn, adapt, and solve complex problems makes them a cornerstone of artificial intelligence. By understanding their fundamentals, you're well equipped to explore, innovate, and contribute to this exciting field. Thank you for joining this journey into the fundamentals of neural networks.